Hi Suresh, hi Veer. So let's start the session once others can join in between. Okay, so let me share the whiteboard. Can you see the whiteboard? Suresh and Veer?
Yeah, it's loading. Yes.
Great. So in the last topic, we were discussing about binary trees, and today we will discuss about the binary search tree. Okay, just a second. Yeah. So binary search tree is an extension of binary tree. So I explained some problem like in the last session that we can solve most of the problem of binary tree through recursion. But in the last session, we solved some label order traversal and all, where we didn't use the recursion concept. So today's session we will cover like some questions on BST, and the most of the question will be related to the recursion. So with the BST, we will also cover the concept of recursion. Okay. So BST, if I talk about the BST, so sorry, BST means binary search tree. So we know about the binary and we know about the tree, but we have this search. So as we already discussed about the binary search, so it is similar to that binary search. Here we have this data in a particular manner so that we don't need to worry about the searching. So for example, let's say we have some value, let's say 3 5 9 2 1. We have these values, so this will be arranged in a tree like this. Let's say we can pick anyone as a node. So let's say 2 is a uh, uh, root node of this tree. So uh, all the element present in the left side of this tree would be less than this 2, and all the element in the right side would be greater than this. So all this 3 5 9 come here and 1 will come here. Okay, so that would be the structure of binary tree, sorry, binary search tree. And we also see the balanced binary tree. So we have this binary search tree and balanced binary search tree. Balanced binary search tree. So balance means we have tree like this: 2, 1, 3, 5, and 9. This is a tree with this with these node, and we can create like this: 3, 2, 1, 5, and 9. This is also a binary search tree with the same data. We can also have like this, 5 3 2 1 9. So we can construct many trees with the same nodes. But if we have a special property that the height of left subtree and right subtree, the difference of left subtree and right subtree would be either 0, 1, or -1. So why -1? Let's say here we can say that length is 1, here 1 2 3. So 1 minus 3, sometime we will get a negative number. So we can say absolute difference should be less than 1, less than equals to 1. So we can say the tree is a balanced tree. Balanced tree means, let's say we have like this structure, like this is the balance, because we have 2 node here and 1 node here. And if we have a tree like this, so anyone tell me this, whether this is the balanced binary tree, binary search tree or not, or we can say balanced tree or not.
Can you scroll actually?
Sorry.
So can you scroll down?
Yeah, you are not able to see this.
So where is your cursor? We don't see it actually. So.
Okay. Okay. Let me create a new page. Just open the second page. Can you open the second page? Are you able to see the second page?
Okay. So I'm just watching in the Zoom link only. I'm not doing.
Okay. So let me share my screen so that you can see the board. Otherwise, you can. Okay. Where is this meeting?
So did you share the link for this actually?
Oh yeah. I share the whiteboard link on the Zoom itself.
Okay.
So, okay, I believe, okay, the whiteboard, you are not able to see, let me open it again. Okay, Suresh, you are able to see this, right? And Veer also, you are also able to see this, right?
Yeah.
Okay, great.
Yeah.
So I'm talking about this tree. Can you tell me whether this tree is balanced or not? This one? This one? Are you able to see this?
So I see only 3 nodes actually. So okay, now I can able to scroll. Okay, I can control this actually. Let's make this.
Okay.
Got it.
So
Now, this is not a balanced tree because like there is a difference of 2 on the left side to compare to right side.
okay, okay. Let me tell you. The height is 1, 2, 3. So height is 3, and 1 and 2. 2. So 3 minus 2 is 1. So is it balanced or not?
Yeah, it's balanced. Okay. Yes, it's a balanced binary tree.
No, but
Okay.
No.
Actually, this is
Because
not
like
balanced.
when I look at the child of the root node.
Yeah. So we should not consider only this part. We should also consider all the elements. So here we have this 2 and here 0. So 2 minus 0 will be 2. So why I am explaining this, because you, for any question, you don't need to like solve the problem for this root. You should also solve for all the nodes, right?
Got it.
Okay, so when I talk about something, let's say if we are talking about the let's take an example. Let's solve a question. So we know that binary search tree means we have a binary tree with this search property. That means all the data would be in a particular sorted manner. That means all so now let's say 3, 2, 1. Okay, then 9, and we need to confirm whether this is a valid binary search tree or not. So is it like it is balanced binary, sorry, or not balanced, this is binary search tree or not? Can you confirm this?
No, it's not a binary search tree. Because like
it is binary tree, but it is not binary search tree. Yeah. How?
At the node 2, like the right side node should be greater than or equal to the root.
Great. So that's why I was explaining this one as well, that we should not think about this root, right? We should also check for all the nodes. So let's start with the same question. Now I just want to solve the problem. I just need to check whether a given tree is binary search tree or not. So let's take a bigger example. Let's say 9, then we have 6, then we have let's say 4, here we have 7, here we have let's say 3, and here we have 8, and let's say here we have 15, 10, 20. So we just need to confirm whether this is the BST or not. So how we can confirm this? I mean, what may be the approach?
So first you can go with the root node and then see the left node. So if it is less than that, then go down and make sure that yeah. So go down and
Okay.
so further go down and yeah. So as the property meeting the criteria. So once you come to 3 and it does not have any nodes, and you can traverse back and 3 is already visited, and then go back to 4 and see the right node. If it's have right node, then it has to be greater than, otherwise again go back and 4 is visited, and going back, and from the 6, yeah, right side is 7, and so that's good. And for 7, it does not have left node, and we are good. And on the right side, it is 8, we are good. And the back, and 9, and we can do the same thing on the right side as well.
Okay, great. Now, think about the same approach, like on the in the programming perspective, how you can write the code for this. Now it would be quite difficult, like because we can see all the node and we can check that okay, whether this is the binary search tree. Just think about, we have a very big tree, so we cannot check every node by seeing it. We just need to write particular code, so that code check the left tree and right tree, right? So let's say we are at here, how we can check whether the tree is binary search tree or not? Just think about the approach, because the code is quite simple.
So what we can do is, like, when you are at root node, try to see, do a recursive loop of is binary search tree of left node, and
okay, you are saying recursive loop.
I mean, like, when at the root
Recursive
node,
function.
yeah,
Because,
recursive function actually.
because recursion is already like when we are using the recursion, I don't think that we need any loop, because recursively we are going for every node. Yeah.
So once you are at the root node, so make sure that do a check, like on the left side it's kind of less than, and right side greater than or equal to. And if it is meeting that property, and again you do the recursive is binary search tree for the left side node, and apply the same property and keep traversing actually.
Okay, fine. So you are saying that I should call a recursive function at root, right? Exactly. So when we are calling a recursive function, we should also check two conditions. First is what would be the breaking state? Breaking state means, let's say if it is null, then we should handle that first.
Yeah, so we can return actually.
Yeah, so we can handle that. And another one, how we are going to call the we have this first corner case, and then the second is recursive call. Okay.
Exactly. And
recursive call
is like
in between we are performing some logic. So this logic is fine. We don't need to worry about this, because we can write this logic. We need to worry about this one and this one. How we are handling these corner cases. So let's say we should not miss any corner cases. And second one, we should call this recursive call correctly. So let's say you are saying that, okay, here we can put the null check, right? Here we can put the null check, no issue. Are you able to see the board, right?
Yeah.
Okay.
So one more thing we can do is, like, basically whenever the condition breaks, you can put a condition.
Okay. Here you are saying that we will check this root node 9. Okay. 9 is so you are saying that 6 is less than 9, so we can check with left side. And similarly this 15, right?
Exactly, yeah.
So we can say this this is passing the condition, right?
Yeah, if left node exists, so if it is left node is less than root, then apply the recursive loop. And if it is
so here just tell me how you are going to write this. Here you have written this logic. You fetch this left node and you fetch this right node, right? Here you have put this condition that, okay, this left node, if left node is exist, so if it less than this 9, okay, and this 15 is this, if we have this right node, so this is greater than this, so that means this node is verified. Okay, only this node. Now you are saying you are calling the function for this, right?
So now I want to do the same thing for the left side actually, until I'll complete all the left side of the root.
Okay. So here I just want to know what you are going to write here. That is the problem. Let's say you are calling, let's say I am calling this f of root. Okay. So here you are saying f of root dot left, right? right?
Yeah, that's correct.
Okay, so this will solve for the left. What about the right? When you are going to solve this like solve this right subtree, so
So
you
we
are
need
saying,
a base condition where like if root dot left equal to null, then we'll return from there actually, and then we start
okay,
handling the right side
yeah,
actually.
those are the corner cases, but which we have already discussed that. Okay, you can handle that. Now let's say we have this we are at 9, so how we are going to move on 6? So we are calling this function like this, right?
Yeah.
Okay, and you are calling this function here. Okay, you are also calling this root equals to, let's say, root dot right. Okay, fine.
Yeah.
You are calling this for left subtree and right subtree. Okay, let's say and you how you are confirming whether all the nodes are valid here. Let's say if we got something missing from here, or let's say after here, how you are going to handle that condition? Let's say we are getting this 21, or
Okay.
let's say we are getting okay, let's say we are getting 8 here. Okay, so is it a valid subtree valid DST? Let's say you are able to find this 9 is correct, fine. Then all these 3 are correct. This 15 is correct because less than 10 is here and 20 is here. 15 is correct. When you come to 10, 0, null, null. So this is correct. When you come to 20, so 8 is less than 20 and we don't have, that means this 20 is correct. And then you come to this, so 8 doesn't have anything. That means this is also correct. But it should not be a case because we have this 9, so it should not come in the right part. How you will handle this case?
You want to
That's
handle
why
that case, then what we have to do is we have to maintain the list of all the nodes from the root to the node what you're doing and all those. Yeah.
okay, 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 okay. So let's say uh, that is a like good discussion, but let's say we are taking an extra space, but just forget about the extra space. Okay, fine. I am taking the list. So what should I take here? From this root till all the nodes, right?
Uh, yeah, I think so. Yes.
So I need to put this 9, let's say 15, 20. Do I need these or only the like root path, like parent of every node, or I also need this 10 and all?
Uh, no, I think I need a traversal of backtracking of from the node to the root actually.
Okay, so I need this list of 9, 15, and 20, right?
Yeah, that's what yes, I'm thinking.
Now, when I checking for this 8, apart from this logic, I also need to search if any element, this element is greater than all these elements, right?
Yeah, yeah.
Okay, so here, let's say whatever the complexity for the whole this recursive call, and so that is the different thing, and we are also checking for this list. So eventually the complexity would be order of n in terms of this list, but in terms of this tree, basically this is the height, so we can say log n, right?
Yeah.
Why log n? Because these are the log n element, because maximum we can have, because this is the binary tree. So all the element which present in this would be log n, because this is the maximum height of this tree. So the time space complexity would be log of n here. This should not be there. We will reduce this, but in your approach we have this extra space as well as we have this extra complexity, because apart from this we are also doing this logic. But you are going in a right direction. Just think about, do we need all these values?
If you able to maintain the smallest element, I think that is fine.
Not a small s. Actually, we need a biggest element here, right? because yeah, here we need this smallest
Like
element.
smallest out of the list, I mean to say.
Okay,
Actually.
okay. Smallest, that means 9. Okay. What happens if we have this 14? Now how we can solve this? This is greater than 9, but it is less than 15. So it should not be the right part of the right subtree, right?
Yeah, I think it's break again.
Okay. So again, we will have some issue with this.
Got it.
Okay. So can we have something that we can store here? We can use apart in place of keeping the list. Can we have a one element from here? But that element cannot be a minimum element or maximum element from this list, because we are not going to maintain the list. But yeah, definitely we should have some element from this list. So just come to this logic. Okay, just come to this logic. Can we include everything here itself? Why we are checking this one? Can we do this here itself? Why we are checking with this 6 and 15? When we are checking for 9, we should check with their parents. We don't have any parents right here, but let's say if here we should check with the value of the parent. So we don't need to keep this this whole list.
Yeah.
Veer Singh, are you able to understand what I am saying?
Yeah.
So basically, the problem, Suresh has given the good approach here, that how we can solve this. We can check every node whether it is satisfying the binary search condition or not, binary search tree condition or not. So we can simply say the corner cases. Then we can check if it is greater than left child value and greater than right child value. Then we can say, okay, this is this node is passing, and we are doing the same process for all the nodes. So it can only take these 3 nodes at any time. Right? It will take only 3 nodes, 6, 4, and 7, and it provide the result on the basis of this. Okay, but let's say here we have this 17. So the 17 is greater than 6. That is right. 4 is less than 6. That is also right. And this all the condition is fulfilling here, but this 17 is not fulfilling the condition because it is in the left subtree of this 9, so it should not be there, right? So that is the problem. If we are going with the current node and the child node, then we are missing the root value, or we can say the parent or 4 parent values. So we should either take the list of all the parents like this, and then we should traverse that whether the particular value is greater than it should be, if we are going in the right side, so we should have the bigger value, and if we are going in this direction, so we should have a lesser value. So either we can go with this list, or let's say we can have any a magic value. Just think about a magic value. I am saying that, okay, if you are here, you just need to check. I will give you the minimum value and max value. You just need to check if it is greater than this min and less than this max. You don't need to worry about anything. Just think that we have these 2 magic values. Now you don't need to worry about the root, parent, or child, anything. You just need to worry about this min and max, and you just need to confirm from that only, right?
Yes.
Now just think about how we can get these magic values. Okay, currently I told you that we have this anyhow, so that's why I called them magic value. But let's think how we can get this these values. Okay, let me give you some hint. We are here, right?
Yeah.
We are here. So let's say we are going to left. Okay, left. So this 6 would be less than this 9.
Yes.
Right. So let's say we are talking about a one value. Okay, one value. Either maybe a min or max. We decided later. So we are here. When we are going to this 6, definitely this 6 should be less than this 9, right?
Yes.
This 6 should be less than this 9. That would be a for sure case. If it is not a case, then we can simply say that this is not a VST, right?
That's correct.
So let's say if we are taking a value, it may be a max or min. We are not saying that. Let's say we have a value 9 for this. When we come to this, one value may be anything, but one value would be not 9, would be 6, because this 6 is also coming from this 9, right?
That's correct.
Because if we are here, this 6 this 6 is related to 9, this is less than this, so we can say one value would be this 6. If we have a 9 here, so we can say let's say we have min or max, so we have, let's say 9 and let's say x. Okay, for this case, just consider this case. So when we come here, so this become 6 and x. Agreed or not? Agreed? Because this 6 is related to 9, so we can replace this 9 with 6, right?
Yeah, that's correct.
Just think that 9 is there. It may be x and 9 whatsoever. Just think about this. We have let's say with the same example, we have 9 and x, and we move here, right? Okay, and this 15 is related to 9, so we can replace this 15 and x, right?
Yeah.
So eventually, if we are going into left or right, one value would be say value would be replaced with the parent data, right? Here we are taking the reference of these kind of things. So we are going with 9 and 15 and 20. So we can replace this 9. We don't need this 9. We can take the 15, right? So it may be, I'm not saying that this would be in left side. Just think that we can change one value. So one value would be same. So it may be x or 9, right? Okay. So now what we need to do, we need to fix one value. One value would be similar to this. And when we are going for the left, we can change, let's say, left value. Okay. And right value would be same. And whenever we are going to right, so this right would be changed. So let's say we are jumping from here to here. Okay. Currently we are going for left. So we will change the, let's say, left value. Okay. When we are going for right, we are not going to change this left value. Let's say it become from 9 to 6. Okay. 6 and x. Okay. Fine.
Okay.
When we come here, so it becomes 6 and x. Okay. When we go right, so we should go this 6 and let's say y, because we are going to right, so we are going to change this value, right?
Yeah.
Right. When I explain the solution, it will be quite easy, but I'm just explaining how we can think about it. Okay. Similarly, if we are going to left, so this would be one branch, and another branch would be, because we are going to left, so that means this 6 become 4 and x. Agreed?
Yeah.
So initially we should just need to worry about this min and max. Okay. Then we should think how we can change this max and min. So just tell me what will be the min and max for this root value. This may be anything, because we don't have any upper value, so this may be anything. Root may be anything, right? From minus infinite to plus infinite.
Yes,
Are you agree with this?
Yeah.
So in starting, we can assume that we can take any value from minus infinite to plus infinite. We can take, let's say we have the constant that, okay, all the value is starting from 0 to 100. So we can say minus 1 and 101. Okay. But for safer side, let's take a max value and min value. So we have like in Java, we have the like a min value and max value, which is the least value of particular range and the maximum value of particular range. So for this, we have anything, right?
Yes.
Now let's come here. So we will check that 9 is belonging to this in between these two. Yeah, 9 is belonging in between these two. So root is perfectly fine. Okay. So eventually every time we will get, we will see that, okay, root is fine. Now let's move to left. Okay. So now this should be like, this value should be less than 9. right? This should
Yeah.
be the less than 9. Am I right or not?
Correct.
Any, this value, this 6 should be less than 9 or not?
Yes. Yes.
Are you like, okay, are you with me that this value should be less than 9? That means the maximum limit is 9. If I am saying that you can eat only, let's say 10 apples, that means you can eat 1, 2, 3, any apples, but you cannot eat more than 10 apples, right?
Understand. It's 9 infinity, you mean to say?
Yeah, so 9 would be the maximum limit, but we have this maximum limit infinite for this. That means for this the maximum limit would be
9.
And this lower limit would be anything, because we haven't defined it yet, right? So minus infinite, what I explained, that one value will change, another will remain same. So this infinite, minus infinite, and 9, right? Okay.
Right.
So I'm creating another board, or let me scroll down. So are you able to see this when I scroll down? Or okay, let me create another page. So page number 2, can you come to the page number 2? Are you able to see?
How to go to page number 2?
Okay. So let me take it. Okay, here on the page number 1 itself. So okay, here we have limit.
Scroll down actually.
Okay. So are you able to scroll down? Just
Yeah,
let me copy this node. 9, we have 6, we have 15, we have 4, we have 17, let's say, and we have 50, 20, and let's say we have 10, let's say 8 here. Okay, that's it. Here we when we are here, so the limit is minus infinite and plus infinite, right?
Yes.
Let's come here. So the limit would be minus infinite and 9, right?
Yes.
So just check. 9 is greater than this and less than this. Okay. Here 6 is less than this 9 and greater than this 6. That means this is done. This is also done, right?
Yes.
Now let's come to left.
Minus infinity to 4 actually.
Yeah.
Minus infinity to 6.
Yeah. So this 9 becomes 6. So we will have minus infinite and 6. Okay. Because maximum limit would be less than this. Okay. What the twist is here? If we are going to write, so this 6 is the minimum value. It should be greater than 6, right? So
yeah,
now this limit will change. So this becomes 6. So whatever value is here, it becomes 6, and this will remain same. So this is 9. So it should be between 6 and 9. Failing, the condition is failed here, right?
Okay, yeah. Now
so we don't need to we did not need to take this 9, 6 and all. We just need to take a particular value. Okay. Okay, someone wants to join. Yeah. Okay, so here now it is quite simple, right? We just need to take care of this particular value, right?
Understand.
Okay. And are you able to understand this?
So when we are traversing, like we have to take a look at the side and yeah.
Like here, we were having this solution, but the problem with we need to take care of this list. Okay.
Yeah,
so,
that's the problem.
Yeah, so we don't need to take this list. What we can do, we can take a value. So the value may be changed for every node. So we just need to take a pair of a value for every node. Here we have this value. Here we have this value. For this we have this different value. For this we have different value. So let's say we are going with the minimum value or maximum value. It won't work. Right. Now let's come to the right direction. Let's say now it would be like 9. Right side means the value should be greater than this 9. Okay, so the minimum value would be 9. So this becomes 9 and infinite will remain same because we don't have any limit. We can have any value. Now, if we are going to left, so this would be the maximum limit. So now here we will have 9. Sorry, not 9. This would be the 9, and the maximum limit would be 15. So 9 and 15, right?
That's
And here we will have 9. Here we will have this 15. 15 would be the minimum limit. So 15 and infinite. Okay, so this is also failing. The condition is also failing here, right?
Yeah.
8 should be between 9 and 15, but 8 is less than 9, right?
Correct.
So now can you write the code for this? Code is quite simple. What we need to do? First, we need to put the null check, and the second, we need to perform the logic that okay, it should be greater than min and less than max, right? And then we should call a recursive function for left and right. Okay, just let me write the code for this. Let me share my screen. Sharing the screen. Okay. Are you able to see my screen? Hello? Are you able to see?
I see the Zoom actually. Yeah, I see a Google page.
Okay. So what was the question? Validate binary search tree. Let's say lead code problem. Okay. So it the code is quite simple. Let me reset it. You can see the code is that much only. So let me reset it. Yeah. So here we have this tree. So let me explain line by line. First thing is, let's say we need a minimum value, right? We need a maximum value, but we already know what should be the minimum value. So let's say we call the function itself. So but in recursive function, we need this min and max value, right? At every stage, right?
Yeah, to keep it as an argument also basically.
Yeah. So we don't have this this value here, right? So we can create our own function. Let's say return is valid is there. So let's say DST, or we can say DFS. Okay, we can say DFS, or let's say check DST. Whatever you okay, VST. Okay. Here what we can do, we can pass this root, we can pass min and max, right?
Yeah,
That's it. But the problem is we haven't defined this min and max. So let's define that min and max. So for simplicity, let's take either we can go with the integer, but let's go with the long. Okay, long dot min value, I believe, right? Min value
underscore value.
Okay, so it will be a min value, and for max we will have long dot max underscore value. That means this will be our min value and this is the max value. Now we need to update every time. So let's create another function, public boolean check VST. So let me copy, so don't make any mistake. Okay, here we will have the node, root, and we have long min and long max. So now we have this function. Now the problem starts, right? Now we need to write the logic. So first thing, if root equals to null, that is the first condition. So we just need to return, or as we are having only single line, so we don't need this braces. So we can simply say return null. Oh, sorry, no, null, true, right? If we don't have any root, that means the tree is already a BST. Okay. Now let's think about it. Now what we need to do, we need to check if we have the left node or right node. Before that, we should check for this root itself. If this we have this value, right?
Root dot val.
Root
Dot val greater than
val is greater than
min.
min
Um,
n.
root dot
So
val less than or equal to max also, right?
root dot val is greater than equals to
Less than or equal to.
okay, less than equals to not less equal to, we are not going to consider equals to, okay,
Okay.
less than max,
Max.
right? What
Yeah.
we need to return? True.
Yeah.
Right.
That's correct. Yeah.
But there is a problem. Let me complete this and then I'll tell you what is the problem. We should not return this. Why? We are checking for validation, so we should not go with the true value, because let's say we are going if we are this condition is fulfilling, we are returning true, so it won't check the left and right.
So rather than going for true, like we have to go for recursive call. Is that correct?
No. What we need to do, we need to go with the opposite. We should check the false statement, not true statement. So whenever we are getting false, we should return it. We should not go for left and right. If we are doing something and then we are returning this, then that is also not a good practice. Why? Let's say we have a tree with 1,000 node. Okay, 1,000 node, and we know that on the second node itself, we know that the tree is not valid. And if we are doing recursion first and then we are returning this, so we will perform all the operations for all the 1,000 node, and then we will return that this value. Okay, so always when you are calling for recursion, always check for the non required functionality. So here we are going for we are checking for true, so everywhere you should return false statement, right?
Got it.
Why we are returning this true then? Because if we have this root, that means we don't need to check anything.
Got it.
We have only this, that's why we have returned this true. So here in place of this, what we can do, this if it is less than min and greater than max, then we are going to return false, right?
And
Any
it's
doubt
our
here?
condition also, right? Basically, it's not an end condition there in between.
Sorry.
It's our condition, I'm saying. So if any one of them fail, like
sorry, yeah, this is or. And apart from this, this is, as we are not considering these min and max, we are going with equals to. Why?
Yeah.
Why? Because we are going for the negation, right?
Yeah, that's correct.
So for negation, we should include this equals to that. Then only we will check for the this. We can exclude these values. But in BST, we have all the unique values, so we can ignore this as well. But let's say we have a duplicate value, then we should go with this equals to, right?
Understand.
But in BST, if you are not going with this equals to, then also it's fine, because we are not going to see any duplicate value.
Got it.
Okay, now let's run a recursion. So recursion should be done on left and right. So what we will do, return check BST. Okay, check BST for tree dot sorry, tree node, not tree node, root
dot left.
Yeah. Root dot left, right? And let's say this will check just forget about this min and max. This will check for left tree. I also check for right tree, and if both are true, then only we should return true. So here we should put and check right sorry, check BST and here we should so root dot right. Okay, are you getting this? We should check for left. If it is returning true, then we should check right. If it is also returning true, then only we should return true. If any one of them returning false, then we are going to return false. Okay.
Yeah, so when you're checking on the left side, root dot left, you have to put the min comma root dot
Yeah.
value.
Here, let's update this value now. Okay. So when we are going for left, if we are going for left, so all the value would be
Minimum.
less than that particular value.
Yes, that's correct.
So that means the max value would be fixed. So max value would be min would be same. We are not going to change min because we are going for left, but the max would be
root dot value.
Root dot val, right?
Yes,
Let
that's correct.
me do it in. And when we are going for right, so it will be root. Oh, sorry. Yeah, root dot val,
Min and
this would be max. So we are not going to go with the changing max value. That's it. Okay. So if I run this, let's see if we are getting any compilation error or anything. Accepted. Let me submit it. Okay, accepted, and let's come to the question. Now let's make it DFS. I haven't put DFS. Why? Because you haven't learned this DFS at DFS. We will learn this in the next class. So DFS is a depth first search, and we in the graph we will see two parts. One is depth first search and one is breadth first search. BFS, DFS. So let's say let me come to the whiteboard. Can we come to whiteboard again? Let me open the whiteboard.
Loading actually.
Yeah. Okay. So it's loading. So when we are going, are you able to see this whiteboard?
Yeah.
Hello?
Yes.
Yeah. So here we are going for left and left. Sorry. Left and left and left and left, and then we are going for right here. That means we are going till the depth, and then we are going for the another depth, then another depth, then another depth, right? That's why it is known as depth first search. And in the previous session we solved some problem related to this what should I say, binary search, binary trees, where we have searched for these label order travels. So this level, right? Hello.
Yeah.
So in the last session we solved some problem related to the level, right? In the first level, in the second level, in the third level, we have solved some problem related to the label order, right?
Yes.
So that is known as BFS. That means breadth first search. And when we are talking about DFS, so DFS means we are going till the end for particular route or particular path, and then we are coming back and then searching for the next path. But don't worry about this BFS and DFS. We will cover these things in the graph itself. Okay. So let's come to the second question. Can you tell me how we can insert particular data into a BST? So let me scroll down the whiteboard and let me write a tree. Let's say, are you able to see this new tree? 2, let's say 9, let's say 6. Suresh, are you able to see?
Yeah, just now I scroll down, I can see it.
Okay. And let's say 1. Now I want to insert 5. So where should I insert this 5?
5 should be insert left node of the 6 actually.
Okay. So 5. So how you can write a program to insert this node? First thing, you should go to the respective node. So let's say if you are here, you should check whether this 5 is greater than or less than. If it is greater than, then go to right. Otherwise, go to left. Okay.
Got it.
So we it is greater than, so we come to 9. Then again check if this is greater than 9 or less than 9. Less than 9, so go to left. Again 5 is less than 9, less than 6. So go to this left, but before going, just check if we have this null or not. If we have this null, we should simply put 5 here. If we don't have null, so we should keep on like going, right?
Yes.
So I believe you can write the program for this. Like you can either go with the iterative approach or you can go with the recursive one. So recursive one would be good. Like it will be of around 4 to 5 lines, but the recursive one would be would be a hectic for you. If you are good in recursion, you should follow the recursive. So you just need to check this condition. If it is null, you should simply return this one as a root because we don't have null. Because we don't have
Here
any root.
also we have to maintain the min max, right? Basically.
No. We don't need anything. What we need to do, we just need to check with this. When we are here, we just need to check if we have anything here. If it is null, then this 5 would be root. Okay. Fine. Now let's compare this 5 and 3. So 5 is greater than. So just call the recursive call for this 9. Okay, let me look. Are you able to understand the logic? Let me show you the code. Let me share my screen so that you will because I don't have much time. So I'll cover this and next question. So let's say the question is related to what? Insert. Okay, insert into binary search tree. Let me show you the code here. If I have, okay, I don't have the code, I believe. Let me go for submission. Okay, I don't have the code. Fine. So in that case, I haven't complete this. Okay, so what we can do, just come to the whiteboard. I'll explain here itself. Okay, here. So just, are you able to see the whiteboard?
Yes. Yes.
So let's say we have a function f, or we should say insert. So we have insert function. So I'm saying I, and here we are having this root. Okay, or we can say node. One is root, and another is node, which we are going to insert. Right. So we have two values. So first we check if root equals to null. That means we should return this node itself, right? Any doubt here?
Yeah, exactly. Because there is nothing, and whatever there is nothing that's going.
Great. Now, if root dot value is greater than node dot value, then what we should return? Return this I insert root dot, if the root value is greater than this, that means it is less than, so we should go for left, right?
Yeah.
Root dot left, comma node, that's it. And else, or we can say without else also, we can say return I of root dot right, comma this node. Are you getting this? Any doubt here? That is the code.
Here, suppose like I want to insert 8 actually, right? So 8 is coming in between the nodes, right? Basically. So how do we store?
You are saying 8.
Yeah.
So what we will okay, let's run the code one by one. So this root is not null. So we compare this 8 and 3, right?
Yes.
So we will come here. This is greater than root value is not greater than. So we'll come here. So we will come here. That means we come here with this. We will come here. That means in the right. So we will come with the 9 and look. Okay. First we will come with 3 and 8. Okay. And when we come here, we will go with this 9 and 8. Right.
Yeah.
So it is also not null. it is 9 is greater than 8. We are coming here,
Yes.
right? So that means we are coming here 6 and 8, right?
Yeah.
After this 6, let's say 5 is not there, or let's say 5 is there, no issue. 6 and 8. So we will come with this 6 and 8. So we have this not null. We have 6 is root. We will go for right, right? Right?
Yeah, yeah.
So now we will come up with the this null and 8, right? Right?
Yes, yes.
Now we will return this node itself. So node 8 return, and where we are returning with the right one. So it will link directly. Oh, I missed this here. We are returning this. Let me write this. We are returning. Let me rewrite this. Return root dot right equals to null. This I root dot right comma node. Okay, that would be the case here also. We are not doing this. We are not returning actually. We are doing root dot left. Getting?
Yeah.
So here, until and unless we are jumping to the next one, we are not doing. At the end, we are returning this node, right? So this node will link to the right child of that node, right?
That's correct.
So that's how we can. So should I write the code for this, or you got this?
Yeah, yeah, I got it. I got it.
Oh, okay, great. So let's cover one more question. We don't have time, but let's take another question, right? So the next question is, let me check for the portal itself. We have some question there. Where is the portal? Okay, track. Okay, so we have validated binary search tree. Yeah, converted sorted list to binary search tree. Let's come to this question. So we have a okay. So if we have just scroll down this whiteboard. I'm writing this. We have 1, 2, 3, 4, 5, 6, 7, 8. Now I just want to or let's say 9. I just want to create a binary search tree with this. So the best way would be I should pick the mid element, right?
Yeah.
And become the root. And now this will be the left subtree, left tree, and this would be a right tree, right?
That's correct. Yeah.
Again, I should pick the mid element and again make a root for left subtree 2, and this would be 1, and this would be 3. So either we can go with 3, 4 or 4, 3, whatsoever, right? Here again, we will have this 7, then we will have this 6 here, and then we will have this 8 and 9, right? That would be the binary search tree, right?
Yeah.
Now, if it is an array, then it would be quite easy. What we can do, we can take a mid element every time. We can break this array into 2 parts, left and right. And every time we can break this array and go on. Now, let's see. Now it is a list, linked list. Then how we can do the same operation?
Then we have to find the middle element.
Yeah, great. So for finding mid, I explained the 2-pointer approach, right?
Yeah.
2-pointer approach, I have explained that we can go with this 1, 2, like we can find this mid. So every time we just need to go for mid, and then we should break this list into 3 parts basically. This would be a right list. This would be a left list, and this would be a root. Again, do for this list. Again, find this mid element and go on. So I believe you can solve this problem as well, right?
Yeah, sure. Got it.
Just try to write the code for this. Okay. And apart from this, Suresh, you can, if you have any question, then you can ask. Otherwise,
Actually, last week I did not attend. Do you have the link for the recording?
so I like we have the recording on the portal. Let me just a second.
Okay, sure.
Okay, let me share my screen. Yeah, are you able to see my screen?
It's still loading. Yeah, I can see it. Yes.
Yeah. So here, let me drag it into down. So here, you can create create up your profile here, and you will see, I believe, in the tree. This is a tree. Let's say best coding. If you go for this tree, okay. So if you go for tree, here you will get this recorded session. Yeah, here you will get this recorded session, last session. So you can follow this session if you want. You can so you can play from here itself. And like about the paid courses. So let's say if you want to select want to give some mock interviews and all, you can schedule your session from here. Not yeah yeah So let's say if you want to schedule some mock interviews from me, so you can schedule from here.
Got it.
Okay.
Got it. Mm-hmm.
So mock interviews means, let's say mock interview means let's say if you are going for an interview, so what kind of question you may may see in the interview. So we will run a same interview, but it won't be a real interview. It would be a mock interview for your practice. And I will also upload even whoever is taking your session, these interviews, they will upload your score in the portal, in this portal, so that hiring managers can check your score and directly contact to you. So it would be great if you create your profile here. You can in this profile, yeah, here you can put like all your detail, your resume, your project, your experience and everything here. So it will help managers to search for you easily, and they can directly contact with you. So you can create your profile here. And if you want to schedule for mock, let's say if you are ready for the interview and you just want to practice one or two mock interviews, so I'll suggest you when you are going for an interview, you should at least take 2 or 3 mock interviews, so that you will be ready for all kind of questions in the real interview. Okay.
Understood. Understood. Okay. Thank you so much. I'm good.
Yeah. And apart from, let's say if you want any help, so you can contact with Rahul. And if you want to know, like someone was asking about the paid courses detail, so let me show you. This is the link of related to the paid detail, what this course have everything. So I'm sharing in the Zoom itself. So if you want to check, okay. So let me stop sharing my recording and then check. Yeah, so here you can find this video if you want to check. Okay.
Okay, sure.
Yeah.
Thank you so much.
So let's meet on the next session.